Hello, good morning. Welcome back. Okay, so today we're gonna talk about deep neural network. So compare with the previous chapter or the previous slide, we can see that the only difference here is we have the word deep before neural network, and just guessing from the title, we can know that now we need to. What we are going to do is to put a lot of layers of single neural network layer together to compose a very deep model. Okay, so intuitively speaking, a deep neural networks that have multiple layers, it should be more powerful in capturing the hidden patterns in data because we have more parameters. We simply have more parameters because one layer in neural network, it's associated with one weight matrix W and a bias B. So multiple layers simply means we have multiple parameters. Okay, so it's a very intuitive thinking that we stack neural networks together, and but in practice, this design of very deep models needs to be carefully tuned because there will be issues regarding the gradients, regarding the magnitudes of the gradients, like the gradients being backpropped through the last layer to the very beginning. The gradients might exchange, the gradients, the magnitudes of the gradients may change very dramatically. Okay, so and a lot of other tons of details, tons of issues that may occur when we deal with deep neural network model. Okay, so but all the efforts that people put into tuning the deep models are totally worth it because deep models is proved to be more powerful in a lot of classification tasks. And today we will only cover the deep neural network composed of feed-forward network, which is the neurons in which the two layers are fully connected. So all the neurons in the second layer is fully connected to the previous neurons. So this is a type of model that is first developed by computer scientists, but for tasks like computer vision, we need a specialized or a special type of neural network called convolutional neural network, and that convolutional neural network can also be put into a very deep models, which is called deep convolutional neural network. But that deep model is not what we are going to cover today. But that is pretty important content which comes later after we have covered convolutional neural network first. Okay, so yeah, so that said, the content today we'll still talk about regular neural network, which is feed-forward neural network. Okay, so let's go to the first slide. And this is a two-layer neural network that has the input data, which we can call it a layer 0, and we call the first hidden layer layer 1, and the second layer the output layer. Okay, so what if we just we add the number of layers, we add the number of hidden layers. Okay, so in this case, if we have the first hidden layer here, second hidden layer here, third layer, fourth layer, and the fifth layer is the output layer. So this is how we simply construct a 5-layer neural network. So it is nothing too fancy. Okay, so it's just the increase of the number of layers. Okay, so in terms of its the forward pass and the backward pass, how we update the parameters, we can draw some analogy to the shallow neural networks. Okay, so we basically adopt the same notations. We use the letter L to indicate the number of layers. In this case, we have 5 layers, and we put that lowercase l as a superscript within brackets, within the square brackets, to indicate the number of, to indicate which layer it is. Okay, and this n superscript l is a number of units in the layer L. Okay, so in this case, we can see that the n1 equals 4, n2 equals 4, and so on. Okay, and we also use the same notation A to indicate the activation for that particular layer L. Okay, and the W and the B's, similarly, they are the parameters associated with layer L. Okay, so these are totally the same with the shallow neural network. Okay, so let's now go over the forward pass and backward pass really quick, which is basically the same thing that we have covered in the Backprop chapter. Okay, using a single example, single data point as an example, so we can compute the Z's and A at the first layer like this, and we add an activation function G1 to Z1, and then we compute Z2 and A2 in a similar way, right? Until so the general principle applies to each layer L, right? So as long as you make sure that in computing ZL, you use the AL-1 as input, and you compute AL by applying a activation function to ZL. So that is what you need to do for each layer. Okay, and if we vectorize it by stacking n data examples together, then the X becomes a matrix, but it doesn't change the appearance. It doesn't change the form of the equations. But the only difference is that now the Z's and A's are also matrices. Okay, so far everything is exactly the same as the shallow neural networks. And now backward step, back propagation, and it's all basically the same thing. So in this case, it's a binary classification. We will have one single value y hat as the prediction. So we can use this quantity to predict the gradients for the last layer, which is the layer 5. So we can first compute the gradients for dA5 and then dZ5, okay? And we use the rule of backprop to compute the gradients for dW5 and dB5, okay? And then the gradients will backprop from layer 5 to layer 4. So we will need to compute the dA4, okay? Use the dZ5, okay? So the dZ5 at the layer 5 will be backpropped here to help you compute dA4 and then dZ4. And these values will be further used to compute dW4 and dB4. And in the computation of dWs, we also need to use the activations from the previous layer, okay? From the previous layer. For dW5, we need to use A4, and for dW4, we need to use A3. So these are just the same principles as the backprop algorithm, okay? So the single example is the general principle here, right? And for the vectorized examples, we basically use the same rule by changing all the notations of A and Z to matrices, to capitalized A and Z. And it's a bit different when we compute DWs because we need to use the average value, okay, by applying this 1 over n. And for the dB, we use the function provided by np.sum by indicating the axis, tell it that we want to sum over the rows by reducing all the columns. Okay, so this is also no different from the backprop in the shallow neural network. Okay, all right. So one thing we may pay attention here, we need to pay attention here is that, as I mentioned in the example here, when you compute dz, you need to use the z5. When you compute dw, you need to use a4. And these z5 and a4, they were computed in the stage of forward pass, right? So that means when we are in the backward pass, when we want to compute the gradients, we need to reuse the values that were computed before in the forward pass. Okay, so after the forward pass is done, we need to keep those values. We don't want to toss them away. We want to keep those activations. We want to keep the z's, the a's, because they will be used in the backward pass. Okay, so this is from a perspective of engineering. So in order to implement a successful backprop procedure or backprop algorithm, we need to keep those values in computed during the forward pass. Okay. Yeah, in this case, the Z5, no, Z5 is a I would say Z5 is a single number, because the layer 5 only have one units, but Z4 is a 2 by 1 vector. So actually Z4 is a 2 by 1, and only Z3 is a 3 by 1 vector, because that's the shape of these depends on how many units you have in each layer. Okay, so now I will look at this process more carefully, with more details. If we look at a layer that's in the middle of a network, it's a general layer L. Okay, then when we compute the activation A, right, we need to use the activation from the previous layer, which is a L minus 1. Okay, so after ZL is computed, right? ZL is WL times AL minus 1 plus BL. We need to store it later. We use the term cache. We need to put it into cache by store it in memory, and because it will be later used in the backward stage. Okay, so in the forward stage, we need to use the DAL as inputs and outputs DAL minus 1. And in this computation, we will need to reuse the cached ZL, okay? Because of the formula we have defined for the backward propagation. The ZLs cached here will be used here, and the AL minus 1 will be also used when we compute DWs. Okay, so if we can simplify this process using computation graphs, then we can use some blocks to indicate the computation that happens in each layer of a deep neural network. Okay, so we can simplify the layer. Instead of drawing a bunch of circles to represent the neurons, we can just use a module or a block or a box to indicate what's happening in that layer. Okay, because we really don't need to draw each single neurons. Okay, so for that layer L, we just pay attention to the inputs and outputs. The inputs AL minus 1 is the activation from the previous layer, which is layer L minus 1. And the current outputs AL is activation for the current layer, okay? And all the parameters associated is WL and BL, okay? So the green arrows here indicates that this is the forward pass, okay? When data flow from the input end to the output end of a deep neural network, we let it go through the forward pass for first, and then we need to cache the activations AL-1 and the ZL, okay? Because these quantities will be used in the later backward pass, okay? In the later backward pass, we will take the inputs. Look, note that the arrow, the red arrow is flipped around, is from right to the left. The inputs is the gradients of AL, which is DAL, and the output it needs to compute, which will be further back propagated to the further layers before it is DAL-1, okay? In computing these two quantities, we will need to use the values here in the cache, okay? So that is the basic computation graph for one layer in a deep neural network, okay? And also for each layer, the DW and DB also needs to be computed because these will be used to update the parameters within the parameters of this layer itself, okay? So having these building blocks, we simply needs to stack them together, right? So that's layer one, okay? Now we don't draw the neurons, we just put this box here and say this is the layer one, and outputs from layer one will be fed into layer two, right? And layer three, and then until the last layer, okay? Assume we have capital L that many layers, okay? And in the output layer, we'll compute, we'll generate some outputs y hats, and this y hat will be compared with the actual label. Then the DAL, which is the gradient for the last activation, will be computed, and the these gradients will be used in the backward step to compute the DW and the DBs, and the backwards propagation will go through from the last layer to the first layer in the beginning, okay, until we reach the input layer, okay? And along the way of back propagation, all the DWs and DBs are computed, okay? And those parameters are used in gradient descent to update the parameters. Though those gradients will be used to update the parameters, okay? So the alpha, right? Just to remember the alpha. Alpha is the learning rate, right? It controls the step, the size, the step size. It controls how much we want to update the parameters using the gradients. Okay, so that is a complete workflow of a deep neural network, how it works from forward to backward. Okay, so in the programming assignments of deep neural network, we gonna implement a neural network, deep neural network using Python, and we will need to implement the basic building blocks like the linear forward function. Okay, so the linear forward function compute. Yes.
Sorry, can I ask a question about that previous slide? So it looks like, does it just go round and round basically? Like you have your forward pass and then you kind of do the backprop to figure out, I guess, how good your parameters were and tune them, and then you like start the process over again.
Yes, yes. So one pass is something we call one iteration, okay? Or if the data is in a batch. Okay, so first of all, the example I showed here use the lowercase x, so that's just one data point. So in practice, what is fed into the layer, first layer, is a matrix or is a batch data. So that batch, we call it a mini batch. So that's part of the data. So that mini batch is fed into the model, and the model computes some prediction, right? Y hat, and this Y hat is used to compute the loss, and the loss will determine the gradients for the last layer, and then all the way from the last layer to the first layer. So that's one iteration of this mini batch of data. Okay, so in practice, we'll almost sure that we will need to have multiple batches, multiple mini batches, multiple iterations to train the model. Yeah, so the updates step occurs after each mini batch is fed into the model. Okay, so when the second mini batch is fed into the model, some new gradients will be computed, and the parameters will be updated using the gradients computed from the second mini batch.
I see. So it's kind of like you're grabbing a portion of the data again.
Yeah.
Run it through. The parameters aren't whatever they were initially there. What we're updating or tuned. I see.
Yes. Okay. Yeah. So a different mini batch means a different proportion. Yeah, I like the way you put it. A second mini batch is a second proportion, just another different proportion of the data. But the whole process is random because we scrambled all the data. So we will need to monitor this process by looking at how much the loss is. So the loss is basically the difference between the Y and the Y hats. Okay. Within this iteration process, we need to monitor this loss. Hopefully we want to observe the loss to continuously drop. Okay. And also we need to use a validation data set to avoid overfitting. So the loss at some point may start to increase, and that is where we need to stop.
Right. Okay.
Yeah. No. For Ron's question, for the next iteration, we don't use the same mini batch because typically our data is very big, and in practice, it's not practical to put everything into a mini batch. So a mini batch usually is just one proportion of the total data sets, of the total training sets. So within the next iteration, we are going to use a different mini batch. Okay, so yeah, in later slides, we will talk about the practices, common practices, how we segment data into mini batches. Okay, so we can look at the Python implementation for the linear forward function and forward function. So in the linear forward function, as the name indicates, we are computing the linear components or the linear combination, which is the dot products or the matrix products between W and X and plus B, right? But here we need to cache everything, okay? We not just cache A, but also the parameters B and W and B is just for the convenience of later backward stage, okay? And it will return the Z's and the cache. And in the forward function, so this forward function, it incorporates the linear forward, okay? Because the linear forward is the left half of the circle, and the nonlinear activation, which is ReLU we use in this case, is the right half of the circle, okay? And they both have cache, okay, stored, and all the cache will be returned because we want to save them in the later stage of backward, okay? So these are just two pieces of sample code, and more complete examples will be provided in the assignments template code, okay? Okay. So in the backward stage, also it comprises of two steps. So the the total backward step, it includes the ReLU backward here, okay? And because now we are going from right to left, so we should do the ReLU backward first, and then use the results dz to compute the linear backward, okay? And in both two backward steps, we need to use the cache, A cache and L cache, which is returned by the forward function, okay? So the backward will determine what is the gradients for the previous layer, for the previous activation, and the gradients for the current W and B parameters, okay? So it's basically a very modularized, and all these linear forward, linear backward, and backward, these functions are applied to each layer, okay? Each layer is basically the same thing happening, okay? So maybe one difference could be the activation functions. Some layers may use ReLU, some may use sigmoid or 10H or something, okay? All right, so, and everything is much more easier if we use a framework like PyTorch. So in the previous video, we also had some examples shown here in the slides that we can simply define the parameters, simply define the weight matrix, the B's, and the forward pass is automatically done, and the backward propagation is also automatically done, and the gradients will be provided to each parameters defined, okay? So in PyTorch, we basically define tensors and use the tensors to store the matrix, to store the weight matrix and the bias terms. And when we define the matrix, we need to let them require grad by setting these requires gradients to be true, so that the gradients will be attached to those variables. Okay, so I'm not going too deep into the details here, but it's more like the backward step is really easy to implement using PyTorch. So here the prediction, the forward pass is defined by defining the computation you want to do. So basically, you want to compute the matrix product between W1, which is your weight matrix, and X is your data, and the clamp function, which is implements the ReLU because it's cut off everything that's below 0. Okay, and then it's apply a second matrix multiplication between the second layer parameter W2. Okay, and the loss is directly computed as a in this case it's a mean square error loss. Okay, and the loss, after the loss is defined, then you don't need to compute the gradients manually, but you simply call the backward function. Give me a second. Okay, I need to leave for 1 minute. Sorry about that. I will pause the chat. I'll pause the record. So after the backward function is called, then we can observe the gradients that are associated to each parameters. So W1 is defined by setting the requires gradients to be true. So after the loss, after the backward step is done, then we can observe some gradients that are attached to the W's. Okay, and after so these two lines of code is a manual upgrade on the parameters, right? It's the gradient descent step that we defined by the mathematical equation, by the expressions. Okay, so this learning rate is just the alpha. Okay, and after the gradients are after the parameters are updated, we can simply manually set the gradients back to 0, because now it's another round of iteration. It's another iteration of computing the gradients. Okay, so this simple example shows a very a introductory level usage of PyTorch, because we are still updating the parameters manually, but in practice we can have different type of optimizers that can be used that do the gradients that will do the updates for parameters automatically for you. Okay, so which we will cover in the later stage. Okay, so that's pretty much we need to know about deep neural network. So it is a very natural extension of shallow neural networks. And typically it works better in terms of performance, in terms of accuracy, if it's a classification task. So why deep models work? They're still researchers curious about these questions, because it's not like fully explained in theory. People use information theory to explain why deep neural networks model works, but there are still different discussions going on. Okay, so one common belief is that the parameters or the neurons at the later stage, which is the deeper stage, they are able to capture some higher level features. So for example, in this task of image of the facial image recognition or face recognition, okay, so the target is to recognize whether this is a face I know or not. Okay, so we have multiple layers in this deep neural network model. So it is commonly believed that the shallower neurons are able to capture some primitive features, like the edges in the image, like the edges at different angles. Okay, so they are captured by the shallower layers, and the higher layers, they are able to capture the different parts on the face, like the regional area here, like the different parts of your face, like the nose, mouth, part of your eyes, the eyebrows, and so on. Okay, and the final or the last layer, or the layer at the later stage, at the very end, they are a more higher level representation, or comprehensive representation of your whole face. Okay, it comes with it basically develops into a representation in some latent space, okay, in some latent dense vector representation as the representation for your whole face. Okay, so that is the common explanations of why deep neural network works better in capturing features in images, in image detection or image captioning, because shallower neural networks doesn't have that capacity in capturing the higher level features. Okay, so after this part, deep neural network is done, we are now going to look at a lot of tricks in order to help us better train a deep neural network. So we need to make the gradient descent process more efficient, and we want to train a deep network effectively by updating the parameters in a proper way. And also, other than the parameters, we have a bunch of hyperparameters to tune. Okay, so first of all, the two concepts, parameters and hyperparameters, they are different. So in the deep neural network, by parameters, we usually refer to the W's and B's that are associated to each layer. Okay, and for the hyperparameters, by the term hyperparameters, we actually refers to the constants that we define at the beginning. Okay, when we set the stage for the model, we need to define a bunch of constants like the learning rate. Okay, so these values, these variables can be changed. They can be changed manually within the training stage. Okay, and also like the number of iterations, mini batch size, number of layers, number of neurons in each layer, what activation functions, and like in a particular task like in NLP, we need to define at what frequency threshold we need to set a cutoff. So like these parameters is something that we need to choose, we need to define before the training stage happens. Okay, so it's also, this whole process is a tricky process because a lot of the knowledge we have right now are coming from directly come from the experience, from the empirical experiments. Okay. All right, so let me skip this a bit. So let's go to the parameters first. Okay, hyperparameters first. So initially, we want to define the learning rates alpha. Okay, so the alpha, I think when we first introduced the gradient descent, we say that alpha is a variable, the quantity that determines how big a step is in each iteration of the gradient descent. Okay, so we'll need to define other hyperparameters, like we will introduce the term momentum, and we will define what is an atom optimization algorithm. Okay, and we will look at how we need to adjust the learning rates decay, how we want to change the alpha gradually during training. Okay, and also mini batch size. Okay, so in order to start, let's do a brief review of what a gradient descent is. Okay, so we have introduced 3 types of gradient descents. Batch, which simply means we put all the data in one batch, and we use all the data to do one iteration of parameter updates. And for mini batch, we segment the data into smaller proportions, smaller parts, and we call each part a mini batch. And the stochastic gradient descent is a rare case that we almost don't use because it only uses one data instance for each iteration. Okay, so let's look at the practical way how we implement the mini batch or how we cut the total training set into different parts so that each part can be a mini batch. Okay, so imagine we have 2 millions of data points. Okay, it's just impractical to put that many data into your memory. Okay, so we need to, for example, in this case, we split the training set into mini batches of size 1000. So in each mini batch, we have 1000 data points. Okay, so let's use an example here. We have all the data points from x1 to xm, and this this m maybe 2 million or 1 million. It's a very large number anyway. So for example, we can make the first 1000 data points as the first mini batch. Okay, and now we use a different notation, like the one in these curly brackets, like one in these curly brackets, and then the x is capitalized. So we use that subset of x to indicate this is the first mini batch. Okay, and we have x2 and x2000. Okay, so this is x2000, right? Because in this case, m is 2 million, and 2 million divided by the size of mini batch 1000 is 2000. So the total number of batches is 2000. Okay, so we have a question: how many observations is considered too many for batch? What is typical? I will come to that part later. And typically, we choose below a number below 1,000. Okay, and that number is determined by the nature of your data. So if each data point is only cost a very small memory space, then we can make a mini batch larger. Or if the model is a not very big model, then the mini batch can be larger. But if the model is too big, then it's less likely to have a mini batch of too big. Okay. And in this case, we have 2,000 mini batches in total, and each mini batch contains 1,000 data points. Okay, and in order to train that model, we also need to segment the Ys, the labels, also into batches. Okay, because the data points they are in a 1-to-1 map relationship. Okay, so we need to have the Ys also segmented. So this results in 2,000 mini batches in total. Okay. So when we do a mini batch gradient descent, it's like we need to set. So for one epoch, okay, or for one pass over the total data, training data sets, we will use a for loop. Okay, that ranges from the first mini batch to the last mini batch. Okay. And within each step of this for loop, we need to do the forward pass or forward propagation on the mini batch xt here. Okay, so this xt is the t's mini batch, and t ranges from 1 to 2,000. Okay, that's a forward pass, and the forward pass is defined by all the layers in the neural network. Okay, so that's layer 1 until we have the last layer, layer L. Okay, and these processes need to be vectorized across 1,000 examples, because each mini batch contains 1,000 data points. Okay, and we need to compute the cost function, right? And compute the gradients using the label yt. Okay, and use the gradients to update parameters using backpropagation. Okay, so that is the so this one pass over the entire data sets is something we call the one epoch. Okay, so when you train a model, it's a usual case that one epoch is not enough. Okay, but that is also an empirical question depending on what kind of task you are training and how big your data is. If your data is very big, then probably before you reach the end of your one epoch, the performance already stabilizes. Okay, but that also depends on how many epochs you need. It also depends on the how like whether your data is representative. Okay, and you want the data to be scrambled. The entire data sets need to be scrambled and to be randomized before you segment them into mini batches. Okay, but usually speaking, we would say that like 5 or 10 epochs is the usual number we need to try. Okay. So for large data sets, we keep in mind that mini batch gradient descents run much faster than batch gradient descents. And actually, for the batch gradient descent that people put everything into one batch is not practical, is not common at all. Okay. So let's review this figure again. The difference between the mini batch, batch, and the stochastic gradient descents is basically demonstrated in these plots, because in the theoretically ideal case of batch gradient descent, the loss will always decrease. But for mini batch, we will see the jiggerings. Okay, so the loss may go up and down, but with some randomness. But the general trend is that it will decrease. Okay, so that's why it's important to keep track of the loss. Okay, keep track of the loss. So here we use the cost function j, but j is just the summation of the average value of loss. So we can also use loss, the term loss, to refer to this average cost function. Okay, so we need to keep track of the loss and make sure that the loss is decreasing, is going to the correct direction. Okay. So the figure on the right, it basically shows how the training makes the initial points approaching the minimum points. Okay, so initially we'll start here or here or here in the parameter space. Okay, and then the ideal way is to go perpendicular to the direction of the contour lines and directly to the minimum points. But the practice is that we use mini batch, and this will make the training more actually faster, because each iteration will takes less time than batch, but it also maintains a basically correct direction. Okay, as compared to this purple stochastic, totally stochastic gradient descents. And this stochastic descent is more risky in not finding the minimum point. Okay. So now it's the question of choosing the mini batch size. Okay. So in theory, we have the basically you can choose any values between 1 and n. Okay. But the typical, we have some typical values to in practice. We can choose 64, 128, 256. Okay, but depends. I want to say that again. It depends on the model, depends on the data. Okay, so in the most recent natural language processing, very huge models with billions of parameters, the mini batch should be quite small, like 16 sentences or 16 phrases per batch is a more suitable choices for those large models. Okay, and using this even number is to accelerate the training or accelerate the data accessing for CPU and GPUs, because the memory addresses, they are organized in a way that is 2 to the power of some integer numbers. Okay. So the basic thought, the idea or the principle is that we don't want a batch or mini batch to be too big so that they cannot fit into the CPU or GPU memory. Okay. So that's for mini batch. And we have some time left. And today I think I'm gonna cover the next part, which is some optimization algorithms which will make the gradient descent much faster than the raw gradient descent. And this is an algorithm called momentum. Okay, momentum algorithm. Okay, so the basic idea is that we compute the exponentially weighted average of gradients and use these average gradients to update the parameters. Okay, so if it's a raw gradient descent without using momentum, then we simply need to compute the gradients and directly use that gradients to update the parameters. Like by like for W, we need to use the minus alpha times the dw and plus that minus alpha times dw to the w. That's the usual way of gradient descents. But for momentum, we don't use the raw gradients, because this exponentially weighted average of gradients gives us some more advantages in approaching the minimum points much faster. Okay, because the raw gradient descents, it's basically there's some randomness in each mini batch, right? It will approach the minimum with some oscillations. It's not like directly pointed to the minimum points. Okay, so this one blue arrow indicates one iteration of gradient descent. Okay, so this one iteration of gradient descent will eventually lead you to the minimum point, which is the red dot. Okay, but using momentum in each iteration, we will first compute dw and db, right? That is a must. Okay, because that's anyway we need to do the gradient to update the parameters. Okay, but now we need to compute some intermediate variable called, or intermediate quantity called velocity. So this v is the velocity for velocity. So the velocity of dw is the previous value of the velocity times some coefficient w beta, and times some 1 minus beta with the current gradients. Okay, so it's a kind of a smoothed version of gradients. Okay, because it doesn't use the total proportion of dw, but it's only used a small proportion of it, determined by beta. Okay, so if beta is big, then if beta is 0.9, then only 10% of dw is used to compute the current velocity, and the 90% of the old values of the velocity is remained. Okay, so this beta basically controls how bold you want the update to be. If beta is small, then you rely much more on the current gradients. If beta is big, then you rely much more on the historical velocity. Okay, so the same applies to the dB. Okay, for dB, we also need to compute the velocity. Okay, so one direct result of using these velocities, the average values, is that if we use VW, if we use the velocity of dW and dB to update, then the process would be much, the curve would be much easier. Okay, we use those velocity to update the W's. Okay, then in the gradient space or in the parameter space, the path that we approach from the beginning to the minimum point will be a smoother path. Okay, which means we reduce the oscillations. Okay, because it's basically an averaging results. It is the averaged results of gradients that we use to update the parameters. Okay, so by averaging the gradients that points to different directions, we basically reduce the degree of oscillations. We basically removed a big part of the randomness in the direction of gradients, because the gradients can point to one direction at one time and points to a totally opposite direction at the other time. But if we compute the average value of it, then we basically makes it point to a more reasonable direction. Okay, by reducing the oscillations. So we'll look at the formula more carefully in the next page to see why it's called exponentially weighted average. Okay, so for example, in the 100th iteration of the computation, so velocity 100 is the beta times the velocity at 99th step, and 1 minus beta times the gradients at the 99th at the 100th step. So if we keep writing these equations, the velocity at 99th step depends on the 98th step and then the 99th gradients. So if we put all those gradients, all the equations here, and substitute them into one into another, we would have that the gradient, the velocity of the last step, VW at 100th step, can be written as this. It is 1 times beta times the gradients of at the 100th step. Okay, the gradients at 100 step, and beta times 1 minus beta of the gradients at the 99 step, and the beta square times 1 beta with the 98 step. Okay, so because beta is a number between 0 and 1, so that means the history information of gradients, or the gradients, the historical gradients that are farther apart from the current points, they would have a less weights in terms of how much it will determine the current velocity, right? So that's why we call it exponentially weighted, okay? Because we have a beta to the power or something, and that exponential term is determined by how farther apart the gradient is to the current step. Okay, so more weights are given to nearer gradients, but less to the older. Okay, but that also means that we utilize the older gradient step instead of just using the current step. Okay, so if we just use the current gradients, then there's more randomness. The path in the parameter space will be zigzag more to a higher degree. Okay, more zigzags. But if we use a smooth, exponentially weighted average, then it's the path will be much smoother. Okay, so the results of doing this exponentially weighted average will result in the blue curves in this example shown in the charts. Okay, so the actual data points are indicated by the circle points. So if we smooth them a bit using the beta, using the exponentially weighted beta, then we will have a much smoother curves. Okay, so larger beta would put more weight on the previous data and smooth the data even more. Okay, so we can use beta to control how smooth we want the path to be. So that beta is usually a fixed value, and we in practice we don't we just use the default value and don't change that values too much, because the difference of using momentum and not using momentum is already a very big difference. Okay. All right, so yes, each addition value in that sum series will add a higher exponential value to beta. Yes, yes. Beta is not determined using CV. By CV, do you mean cross-validation? Yes, so in practice, we don't actually change the beta. We just use the beta as a default value. I don't recall the number, the default values, because we'll see that the momentum methods will combine with RMS propagation method, and we define a new optimization method called Atom. So Atom optimizer is currently a very standard choice for optimizing the parameters. Okay. So we don't actually change the values for beta that often. Okay. So let's look at the details of how we implement the momentum method, right? So we need to have some initial values of the velocity, okay? Because the current velocity is partially depends on the older velocity values, okay? So within each iteration, we need to compute W and dB, okay? And we compute the velocity for the current iteration. and we update the parameters. And typically, beta is 0.9, and we don't actually change that numbers a lot. So momentum, it's almost always work better than the raw gradient descent or vanilla gradient descent. Okay, so that's momentum. And based on that, let's look at, very quickly look at another method called RMS prop, okay? So RMS prop is the short for root mean square, okay? It's a similar effect as momentum, but it uses a different mechanism, okay? So the result is that, assumption is that there is a relatively big oscillation along the direction of W, okay? And the solution is that we want to decrease the magnitude of the dW, okay? Because it oscillates too much, then we simply want to decrease the magnitude of the dW, the gradients, okay? So in details, this method will need to compute some intermediate variable called s, okay? So this s is something to the velocity, but it's not necessary, it's not exactly the same quantity. We compute some quantity called s, and within each iteration of the mini batch of the gradient descent, we compute dW and dB, and then we use the weighted sum of the previous SDW and the weighted sum with to add with the weighted value of dW square, okay? Because this is the square which basically measures the magnitudes of the gradients, okay? So also for dB, and then we will need to use this SDW and SDB to weight the gradients dW. Okay, it's weighted by the SDW and SDB. So because the dW square is in SDW, so the gradients that has larger magnitude will be curved to a smaller value, right? And this epsilon is for the normalization purpose. It's for like avoid zero dividing by zero problem, okay? So anyway, the dW normalized by its square root is basically a kind of a normalized value. It has a smaller magnitude for sure, okay? So larger dW means larger SDB, and that means smaller actual updates to W, okay? So it's a dynamic updates. When dW has larger values and the actual value that's used to update W becomes smaller. And if dW is too small, then this quantity becomes the actual updates to W becomes larger, okay? So basically to distinguish from momentum, we use a beta with subscript 2, okay? And when these two betas combine together, we have one beta from the momentum method and one beta 2 from the RMS prop method. Then we basically can combine them together and come up with a method called ADAM, which is short for adaptive moments estimation algorithm, okay? So we basically combine two steps. The velocity is from the momentum step, and the S is from the RMS prop method, okay? So for each iteration, we will first compute the momentum, compute the velocity, and we also compute the S value in the RMS prop, okay? And we use beta 2 hyperparameters, beta 1 for momentum and beta 2 for RMS prop. So we need to compute the adjusted velocity, okay? And adjusted S. So this is for correcting the bias and to speed up early stage learning, okay? And we will simply compute the W and B's in this way, okay? Because if it's momentum only, then we'll just put the velocity here, okay? If it's RMS prop, we'll just put the normalizing term here. But now if we combine them together, and we will usually achieve much better effects in terms of training speed, okay? So all the purpose of momentum and RMS prop and atom, they are to accelerate training, to help the optimization process to quickly reach from the initial point to the minimum point, okay, by avoiding the oscillation within the parameter space. Okay, so that's pretty much of the content today. And finally, let's look at this final slide here. In practice, in PyTorch, using TensorFlow or other frameworks, we don't need to implement the optimizations process ourselves. We can just use the defined classes like the optim_, gradient descent, RMS prop, or atom. And usually the atom is the more popular choice now because it combines the momentum and the RMS prop. And usually it trains faster than the standard gradient descent method. And yes, that's the content for today. And I will release the homework, the assignment for neural network. I think it's a shallow neural network assignments. And in the next week, we're gonna do the deep neural network model. Okay. Yes. So for now, we'll use convolutional for the neural network and the deep neural network models. We will use NumPy, but for the convolutional neural network is introduced, we're gonna use something in PyTorch. Okay.